afternoon, everybody. Welcome to your class. I hope everything's going well. Everybody's staying healthy and safe and getting a little bit of work done over the time. Okay? Offer up. If you think of anything that we could do better on these videos, film quality, time, subject matter, send me an email and we'll get them together and we'll get the best product we can put together as a team. Great. Thank you. I'd like to start off with chapter 21, electrochemical. A little bit of review before we get started. A redox reaction, as you remember, it's talking about reduction and oxidation, redox reaction. The most important part of all of our redox reaction is, of course, oxygen. Oxidation, an important prospect of all chemical reactions. So we're looking at our oxygen atom. If you remember back, we had our S shell, which was a circle, 2 electrons in the S shell. Then we have our P shells. We have 3 P shells, 2 electrons for each of the shells for a total of 6. That means that in this level, this shell level, there should be a grand total of 8 electrons. All right, let's see what we got. Oxygen, if you look at the periodic table down here, it's got 6 electrons in the outer shell. So it's got 2 in its S shell. Good. Inside my P shells, I got 1 with 2 electrons. I've got 2 with 2 electrons. Now I have a problem. I've got a 3rd P shell out there, a 3rd dimension that these shells are in. It doesn't have enough electrons to fill it. So it goes out wandering around the world looking for a friend to share electrons with. And it finds this lonely hydrogen. It only has 1 electron. It's trying to make a wheel with its S shell as well. But there's only half of a rim. So this poor wheel's going bumping down the road. Boom, boom. So the oxygen says, hey, let's share that electron. And it bonds inside. Goes and finds another hydrogen. And it says, let's share that electron. So that all of our shells can be balanced, can be full, and we can be a combined molecule together. We'll have these covalent bonds between our atoms so that we feel balanced again. Part of a solid family. And they make their water molecule, H2O. That thing that's all important in our world. Let's start off by talking about half reactions. As we're dealing with our redox reactions, we're really talking about moving electrons. Even when we're talking about our electron here, we're talking about filling that electron shell. All the cool stuff in chemistry happens in the electrons, in those shells on the outside of the atoms. So if I'm looking at my sodium down here in column 1, a sodium, it says to itself, self, I've got a spare electron that I'm willing to share with somebody else. So we write it as a sodium ion with a positive charge and a negative electron out there looking for a friend. If I look at magnesium, for example, that's in the second column. So it has 2 spare electrons. If I write out my magnesium, as it falls apart, I've got an ion with a charge of 2. I have 2 holes looking for more electrons and 2 electrons offered up to a friend. If I'm talking about my hydrogen, this hydrogen, if you see, you can't have half of a wheel. It always has to be together with something. If it's all by itself, it will always be a diatomic 2 molecule. There'll be 2 hydrogens bonded together. So when they split up and they turn into ions, you have 2 hydrogen ions with 1 charge. That means we have 2 electrons that are out there looking for a home, someone to bring them into their family. Depending upon where they are on the periodic table, over here we got 1, 2. Over here we got 1 hole, 2 holes. So often these anions will bond with these cations. If you remember all the way back to last semester, those crazy terms. Okay, how can we apply this to our real life? Because everything in chemistry is about understanding how the world functions. So I have got this guy, Alessandro Volta, all the way back in 1800. If you look at his name, you see Volt there? He's so important that we're naming stuff after him. So obviously this Alessandro Volta came up with these ideas, and he called them a voltaic cell. He says, I wonder what would happen if we put a negatively charged substance, zinc, and connected it to a positively charged substance, copper. Could I make those electrons flow? So this dude's way ahead of his time. Why he cared about electrons moving across a wire, I don't know. But he did, and thankfully he did. So, because today we have taken his idea of these voltaic cells and used them to make our batteries. Thing looks like a C battery to me. Might be a AA, AAA. But you have the positive side and you have the negative side. So we've taken this cathode in the middle. What he used is copper, we use is graphite. But he had this positive rod down the middle of our batteries. Around the outside of the battery, we've got a negative coating, negative casing. That is an anode. We hook up a wire to the bottom on where it says negative. The battery means what it says, the negative side. It hooks up at the bottom of the battery, and a wire allows those electrons, those freed electrons, to follow it all the way around and get to the positive side. So I can have a negative and a positive, and they can make their balance. Fortunately for us, if we hook a light bulb or an iPhone up inside these things, these electrons will go through the light bulb as well. And these electrons will bounce around in there and give us our light, give us our heat, give us our electricity that we use for everything that we need today. So these electrons go through and then go back to the top of the battery. Same thing will work with all kinds of different devices, all kinds of different electric requirements, all thanks to Alessandro Volta. Thank you very much. I appreciate you listening, and I'll be back with you next time with the other half of the Chapter 21 lesson.